Hello everyone, this is part 8 video on past year NEET questions from the topic Electrostatics and Capacitors. Now those who are looking at this video can take a look at the previous part videos so that you will have continuity of questions. We'll start with a question that has come in the year 1998. A point Q lies on the perpendicular bisector of an electric dipole with a dipole moment P. If the distance of Q from the dipole is R, which is much larger than the size of the dipole, means here we have to consider that the dipole is a short dipole. Then the electric field at point Q is proportional to, so we have to conclude electric field is proportional to in terms of the P dipole moment and R. So if you look at it, right, so let us say we have a dipole here, combination of equal and opposite charges separated by some distance. Generally we will take the distance as what? 2a, that is the length of the dipole. Perpendicular bisector means that is also going to be the point on the equatorial plane. So here we are choosing a point at a distance r. The given thing is r is much larger than the length of the dipole. That's why here we are using the short dipole. So here the dipole moment will be from negative charge to positive charge direction, and the value of this will be equal to what? Q times 2a, the charge value into the length of the dipole. So here this is the point. So this is the point where we have to find the electric field. At a point on the equatorial plane, the electric field direction wise it will be opposite to the direction of the dipole moment. So for a normal dipole, right, the field value will be minus kp bar divided by r square plus a square whole power 3 by 2. This is what is the dipole electric field produced by the dipole. If it is a short dipole, means a we will neglect, so it becomes what? Minus kp bar, we will neglect a, means it will be what? R square whole power 3 by 2 means r cube. So the negative significance is about the direction. So what do we see? Just the magnitude, right? Just the magnitude is proportional to P and is proportional to r power minus 3. So what is the correct answer for this? Option D. It will be proportional to P and proportional to r to the power of minus 3. Next we have a question based on the electric flux. This has come in the year 1996. A point charge plus Q is placed at the center of a cube side length L. So let us consider a cube. The point charge is placed at the center of the cube. Side length of the cube is L. So we are keeping the charge at the center. So the cube is as such it is the enclosed surface. The electric flux emerging from the cube means inside the cube there is only one charge, that is the charge Q, right? So the flux will be contributed by only charges inside, that is the Gauss law concept. So flux through the cube is equal to what? Charge inside, which is Q, divided by epsilon naught. It's a straightforward question. Option D is the answer. Next we have another formula question as it is. Energy stored in a capacitor of capacity C and potential V. So if you have a capacitor whose capacitance C and the potential difference across the capacitor plates is V, then energy is stored. What is the energy stored formula in terms of the capacitance and the potential difference? Half CV square. We have three alternative formulas, right? Energy will be Q square by 2C. This is the formula in terms of charge and capacitance. Then we have this particular formula, that's what we are using now. This is in terms of the capacitance and voltage. Then we have one more formula, that is in terms of the charge and voltage, half Q into V. So in this case we are using this half CV square, which is what? Option D, CV square by 2. Two metallic spheres. Metallic spheres means what? The charge will be residing on the surface. Radii 1 centimeter, 2 centimeter are given charges. What are the charges given to them? 10 power minus 2 coulombs and 5 into 10 power minus 2 coulombs. Means one sphere is having a radius of 1 centimeter. 1 centimeter means we can take it as what? 10 power minus 2 meter. Other one is having a radius of 2 centimeters, means 2 into 10 power minus 2 meter. This is initially having a charge of 10 power minus 2 coulomb. This is having a charge of 5 into 10 power minus 2 coulomb. If they are connected by a conducting wire, and by the way, where is this charge going to be for both these spheres? Because they are metallic spheres, right? Conducting spheres. Charge will be on the surface. For both of them, the charge will be on the surface. So metallic or a conducting sphere is equivalent to a spherical shell because they will have charge on the surface. If both of them are connected by a wire, means what? We connect them by a wire. What is going to happen? Charge transfer is going to happen, correct? Final charge on the smaller sphere. Now, how would this charge transfer happen? Because if there is a potential difference between the surface of sphere 1 and sphere 2, if there is a potential difference, means charge will flow from high potential to low potential. So here what is the charge on the first one? 10 power minus 2. Charge on second one? Total charge that is available is what? Because this is the charge that will be distributed. A total charge is what? 10 power minus 2 plus 5 into 10 power minus 2, that is 6 into 10 power minus 2 coulombs. This is the charge that has to be distributed. Now what we'll say is, let charge on 1 centimeter radius sphere is x into 10 power minus 2 coulomb. We are using the same exponential factor. Then charge on the 2 centimeter radius sphere, that will be equal to what? 6 minus x into 10 power minus 2. Because if this is x, means remaining will be what? 6 minus x, right? 6 minus x into, there is a multiplication factor 10 power minus 2. Now what we'll do is we will look at what is the potential on a spherical shell, right? What is the potential on the surface? Formula kq by r. K is the Coulomb's constant into charge divided by r. So we'll just go and substitute. So what is the condition? Once the charge transfer is happening, right? Final state, they both will have the same potential on surface. That is when the charge transfer is going to stop. Means what? Potential on the surface of the sphere 1, which is our 1 centimeter sphere. 1 centimeter means 10 power minus 2 meter radius. K into Q is what? X into 10 power minus 2 divided by R. R is what? 10 power minus 2. This potential should be equal to potential on the sphere 2. Sphere 2 is what? Radius is 2 into 10 power minus 2 meter. K into charge on this will be 6 minus x. Divided by what is the radius? 2 into 10 power minus 2. 10 power minus 2, 10 power minus 2 cancels. K also will get cancelled. X is equal to what? 6 minus x divided by 2. We'll bring the 2 this side. 2x is equal to 6 minus x. Bring the x this side. Minus x will become plus x. Totally 3x is equal to 6. Means x is equal to 2. So charge on the 1 centimeter radius sphere, what is it? X into 10 power minus 2, right? Means what? X is 2. Will be what? 2 into 10 power minus 2 coulombs. What is the correct answer? Option D. They are asking what? The final charge on the smaller sphere. Smaller sphere is what? The one which is having a radius of 1 centimeter. What will be the charge on the larger sphere? Total is what? 6 in 10 power minus 2. This is having x in 10 power minus 2, x is 2. The larger one will have 6 minus 2, which is 4 into 10 power minus 2. But here anyway they are asking only about the smaller sphere, right? So answer is what? Option D is the answer. Next we have a very interesting question. This question is based on the relation between electric field and the potential. There is an electric field E in the x direction, means the electric field E is actually in the x direction. If the work done on moving a charge of 0.2 coulombs through a distance of 2 meter along a line making 60 degrees with the x-axis. So we are moving a charge 2 meter along a line which is making an angle of 60 with the x-axis. From, say, for example, A to B we are moving. In this the work done is what? 4 joules. What is the value of electric field? We have to find what is the value of electric field. See, when you move from A to B, what is the work done? 4 joules. Charge that we are moving is what? 0.2 coulombs. Means the potential difference between A and B, that is what? Work done divided by the charge that is moved, which is what? 4 joules divided by 0.2. Means 4 joule divided by 0.2 means what? We can write 1 by 5. So totally what is the work done? I mean, the potential, potential is what? 20 volt. So charge is in coulombs, so joule per coulomb is what? Volt. So the potential difference between A and B is what? 20 volt. Now this 20 volt potential difference is for a distance that is moved, which is 2 meter. Remember, in any direction the minus delta V by delta L, means negative of change in potential by the distance that is moved, will give the electric field component in the direction. What is it? Any direction. So we'll keep this. What is this? VAB, this is 20 volt. We'll keep this result. Any direction we move a distance delta L, then the electric field component in the direction is given by what? Minus delta V by delta L. The minus sign indicates that when we move in the direction of the electric field, right, the potential difference is going to be negative. So here in this direction, see, electric field is towards the x-axis, right? In this direction, what is the component of the electric field? Electric field component will be equal to what? The angle is 60, right? So electric field component is what? E is the total electric field value into cos 60. We are looking at component of electric field along the direction AB. What is it? E into cos 60. What is cos 60? Half. Means the electric field component in the direction AB is what? E by 2. Now this value, right, what is it? Just comparing the values, what do we have? If you take a modulus, right, because we are only looking at the values. If you take a modulus, means that will give us what? The electric field component along that AB direction. Delta V is what? The change in potential or the potential difference, which is what? 20 volt divided by what is the distance moved here? 2 meters. This is equal to what? The component of the electric field in the direction, which is E by 2. So 2 is cancelled. So what do you get? Electric field is equal to what? 20 volt per meter. We can express the SI unit of electric field in one more way. What is it? Instead of using volt per meter, we can say Newton per coulomb also. So what is the answer here? Option B, which is 20 Newton per coulomb. So all we are doing is we are looking at what is the potential difference between the points A and B, and we are using the relation. What is the relation that is used? This is an important relation. In any direction, the electric field component will be equal to what? Minus delta V by delta L. A charge Q2 is at the center of a circular path radius R. Means we have a circular path of radius R. Charge Q2 is at the center. Work done in carrying a charge Q1 once around this equipotential path. So you see, any point on the circumference, right, will be what? At the same distance R. Means at each and every point, what is the potential because of the charge Q2? K Q2 by R. All these points are called as what? Equipotential points. Let us say we are starting from A and we have to go around and come. So they are saying once round this equipotential path, means we have to cover one full round. So we are going to come back to the same point, right? Which means what? The Potential difference will be what? Final potential is kq2 by r. Initial potential is also what? kq2 by r. So potential difference will be 0. So work done in moving the charge q1 will be what? q1 into delta v, right? That is what? q1 into 0, which is what? Not only that, no, we have to complete one full round. Even say for example we are moving from a point A to another point on that circumference. It can be any point. We'll move from say point A to point B. This can be another question. We'll move from point A to point B. Point B can be anywhere, but still potential of point A is what? kq2 by r. Potential of point B is also what? kq2 by r. So in moving from point A to point B, again there will be no work done, or work done will be what? 0. So what is the answer for this? Option C is the answer. If you complete one full round means anyway definitely the potential difference is 0, so work done is going to be 0. Next we have a fundamental question based on the identification of charges based on the electric field lines. So what is the basic concept here? If field lines are emerging out of a charge, if the field lines are emerging out of a charge, right, what does it mean? That charge is basically positive charge. If the field lines are terminating or ending at a charge, means what? That particular charge must be a negative charge. The given figure gives electric lines of force due to the two charges q1 and q2. What are the signs of the two charges? So the electric field lines can be also called by the name electric lines of force. What are the signs of the two charges? Look at this. q1 lines are ending at q1, they are coming to q1, they are terminating at q1, means what? q1 must be negative. What about q2? Field lines are coming and ending at q2 also, means q2 also must be what? Negative. Means what? Both the charges must be negative, which is our option C. So we'll conclude whether the charge is positive or negative depending upon whether the field lines are emerging or coming out. Emerging or coming out means what? That will be positive. Terminating or ending means what? That will be a negative charge. In this case, both of the cases, the lines are terminating or ending, both for the q1 as well as q2, means both of them must be negative charges. A hollow metallic sphere. Hollow sphere means what? It is the spherical shell of radius 10 centimeter is charged such that the potential of its surface is 80 volt. Means we have a hollow metallic shell. Okay, so it is charged. Now hollow means what? Whatever the charge we give, it will be on what? It will be on the surface. Okay, what is the radius of the shell? Radius is given as what? 10 centimeter. It is charged such that the potential on the surface is what? 80 volt. Remember, for a spherical shell, potential on the surface, potential on the surface for a spherical shell will be kq by r. If q is the charge given to the spherical shell and r is the radius, right? Here the r will be what? Radius. Potential at the center of the sphere would be, now for a hollow metallic shell, the field inside will be 0. So inside the shell there will be no field, which means what? When we are moving from the surface to any point inside, since there is no field, the potential difference will be what? 0. Because when you move along a path, potential difference will be equal to what? Electric field component in the direction. You move any path, right? Potential difference is 0, means there will be no electric field component in the direction. Means what? Everywhere inside the spherical shell, the electric field is going to be 0. So any point you take, the potential at that point will be equal to potential on the surface. It need not be just the center. For any point inside the, so for any point inside the spherical shell or metallic conducting sphere. Now we need to understand the difference between them. Spherical shell means only what? The outer surface. Sphere means you will have material inside the volume also. But if it is a metallic or conducting sphere, right, in that case also same phenomena. Electric field inside is zero means potential on the surface, right, will be equal to potential at each and every point inside. Not just the center, but each and every point inside. They're asking potential at the center of the sphere. It will be what? Same as the potential on the surface, which is what? 80 volt. Next, this is a very interesting question. This talks about the nature of equilibrium. This is a question based on nature of equilibrium. So generally when we talk about equilibrium, right, so we'll talk about these two kinds of equilibrium, stable equilibrium and then unstable equilibrium. What is a stable equilibrium? Like, think about it. If you have a vessel like this, in this we keep an object, we displace it, what we'll observe is the object will have a tendency to come back to the original position. This kind of equilibrium is called as what? Stable equilibrium. If instead you look at an inverted vessel, on that you keep an object, you displace it, the object will move away from the equilibrium. This kind of equilibrium is called as what? Unstable equilibrium. So when you displace an object, it has a tendency to come back to the same point, means what? It will be a stable equilibrium. If you displace an object, it is going away from equilibrium, means it will be called as what? Unstable equilibrium. So this we talk about it more importantly in the case of the dipole. So here we look at what is the question. Point charges plus 4q, minus q and plus 4q are kept on the x-axis. X is equal to 0, x is equal to a, x is equal to a. Means x is equal to 0, x is equal to a, x is equal to a. What are the charges? Plus 4q, minus q, plus 4q. Now the thing is, this combination of charges, right, we have to comment on whether they are in stable equilibrium. Just maybe you can take a look at these options. Option A is saying what? Only minus q is in stable equilibrium. Option B is saying that all the charges are in stable equilibrium. Option C is saying that all of the charges are in unstable equilibrium. Option D is saying that none of the charges are in equilibrium. First we have to conclude whether there is an equilibrium or not. Then we will go to stable or unstable. So to know whether there is an equilibrium or not, first thing is what? This minus q, let us look at it. Minus q is exactly placed at the midpoint between the 4q and 4q. Now the electric fields produced by both these 4q charges, right, at the midpoint will be equal in terms of value, opposite in terms of direction. So because of both these charges, right, field here will be what? 0. Since the field at the midpoint is 0, what is the force acting on the minus q charge? It is going to be 0. Means the minus q is in equilibrium. That we are able to conclude. The minus q is in equilibrium. Now let us try to focus on the other two charges. See, other two charges, they are identical. One is on this side, distance a from the minus q charge, other is on the other side. So here what we will do is we look at any one of them. Let us focus on the plus 4q. This will be repelled by the other 4q charge. It will be attracted by the minus q charge. So what about this force value? K into 4q into 4q divided by distance between the both the charges is what? 2a. 2a the square. That is what? 2a square means 4a square. 1 4 is cancelled. 4kq square by a square. What about the force because of the minus q charge? The distance between them is A. K into 4Q into modulus of minus Q divided by A square. That is what? 4KQ square by A square. We'll see here both these forces acting on the 4Q charge, they have equal value but exactly opposite direction. Both of them are what? 4KQ square by A square. So they will cancel each other. As a result, the total force acting on the 4Q charge will be what? 0. Total force acting on the 4Q charge will be what? 0. Which means the other 4Q charge, they are identical, right? Other 4Q also will experience how much force? 0. So this given arrangement of the charges, first of all, it is in equilibrium. The first conclusion is what? All these three charges, right? The net force acting on each of them is what? 0, which means they are first in the equilibrium. That is concluded. Which means option D cannot be the answer, because option D is saying what? Option D is telling that none of the charges is in equilibrium. This is incorrect because all the three charges are basically in equilibrium. Now the question is whether the equilibrium is stable or unstable. That is the question. So for that, what we'll do is, again we'll look at the representation. So we have a 4Q here, minus Q and 4Q. This gap is A, this gap is A. Now let us look at the equilibrium of minus Q. We'll try to find out whether the equilibrium of the minus Q is a stable one or unstable one. Now the thing is, if you want to prove that it is stable, means we should try and displace the charge in all possible directions and check whether it is coming back to that original place or not. But if you want to prove it is unstable, right, if you can just give one example where if you displace it is not coming back, that is sufficient. Means what? That will be unstable. To prove it is stable, right, we have to prove that in any direction you displace it should come back. But to prove it is unstable, just one example will be sufficient. If in one direction you displace, it is not able to come back to the same path, means what? It is unstable. So what we do is just think about it. We will try to displace the minus Q just to the left side here. We will try to displace the minus Q to the left side. Now it comes here, imagine. This minus Q now is attracted by the 4Q. It is also attracted by the other 4Q, but it is closer here, right? So we have displaced towards left, and from here, look at this carefully. This is a shorter distance, so the force here will be what? Stronger force. Force on the other side will be weaker force because the distance is longer now. As a result, left side stronger force means what? It will keep moving towards the left side. So when we displace it towards the left, due to the stronger force in the left direction, the minus Q will keep moving. It will keep moving away from the equilibrium place. Equilibrium place is here, right? So which means what? This we will call it as what? Unstable equilibrium. Why I picked up minus Q first, I'll tell you. Because look at option A, what they are saying. Only minus Q is in stable equilibrium. This is proved wrong. And look at option B. Option B is saying what? All the charges are in stable equilibrium. This is also wrong. Why? Because we are able to pick up minus Q, and minus Q is clearly in what? Unstable equilibrium. So by this itself, right, we are able to conclude what is our correct answer. So this is how we have to save time while we are really solving in the final examination. So without even really discussing about the nature of equilibrium for the 4q charges, right? We are able to conclude what is the answer for this. So what is the answer? It is going to be option C, which is all these charges will be in the unstable equilibrium. Now we have to check, because the way we are doing this exercise is also to get the practice, right? In future, maybe in the forthcoming years, we have a similar type of question coming. We should know how to approach. So let us look at the case of the 4q charges. So we'll pick one of them because they are identical, right? If we are able to prove the case of one, means other also will be proved. Look at this. What we do is we will bring this. So this distance is what? A. This side is also what? A. We will move it to the left. So 4q charge that we are marking, right, is we'll say displaced. How much? A by 2 towards left. Now the distance from minus q charge will be what? A by 2. Distance from the other 4q charge will be what? A plus A by 2 will be 3A by 2. Now look at the 4q charge here, right? 4q charge will be repelled by force due to the other 4q, will be attracted by the force due to minus q. So look at the magnitudes. Force due to minus q is what? K into 4q into modulus of minus q divided by A by 2 the square, which is what? A by 2 square means it will be A square by 4. 4 will go to the numerator. Totally what is it? It will be 16 kq square by A square. What about the force due to the 4q charge? K into 4q into 4q divided by distance between the 4q charges is what? 3A by 2. So 3A by 2 the square. This is what? 64 kq square by 9A square. Now the question is, which of these forces is higher? Which of these forces is actually higher? See, 64 by 9, that is like what? 7 point something, because 9 sevens are 63, right? I mean, no, 64 by 9 is what? 7 point something. Here what is the factor? 16, which means the force due to minus q is what? Higher one. So force due to minus q is trying to pull it further in the left direction, right? That is a stronger force here. Means what? 4q will continue to move left, which means what? If we are displacing it left, the tendency should be it should go back. That is when it will be stable, right? But if you displace it left, what is the thing we are seeing? The net force acting on this is still in the left direction. It means it will keep moving in the left. So that is also what? Unstable equilibrium. So one 4q is unstable means identical, right? Other one is identical means all the three charges will be in what? Unstable equilibrium. Now again we have to keep one thing in mind. To prove it is unstable, if we are able to take one example and show it is sufficient. But to prove it is stable, right, we have to look at all the possible ways of displacing the charge. Then only we can say that it is stable equilibrium. Okay. So this is about the question about the nature of equilibrium. So with this we have completed the discussion of past year questions from the electrostatics and capacitor chapter. We will see in the next chapter.